M1 is going to slide down this ramp. So gravity is going to go pull it down, but there is going to be friction. Um, it's going to fly off this thing, and this little arrow here might be a little confusing. It is not launched horizontally. It is going to fly off the ramp at the ramp's angle. So this is going to be like a negative launch angle here, right? We're gonna have a vertical velocity that is down at this launch, and again, it's not horizontal, so it's gonna have to have the cosine theta and the sine theta pieces to it. And it's going to cut a string, and that just cuts the string to release M2. M2 is then going to rotate down and smack M3, which is the board. That system is then going to rotate down to the ground, and we want to like how fast it's rotating. It's going to hit some scissors. The scissors going to cut that rope, and then M5, M4, and the pulley are going to be an Atwood machine. And now we have to do the Atwood machine with the pulley because the pulley has mass, and so we have to treat it as different. And then also the tension here and the tension here are no longer the same because we have to apply a torque to the pulley if we're going to rotate it. Now, if we go old school and the pulley didn't have mass, then this is really easy. This is just M5G minus M4G equals, M1 plus M4 plus M5A. But now that we have a pulley having mass, we have to adapt. Okay, so I'm going to walk you through the solution. Okay, so the box sliding down the ramp, that I'm going to use energy for that. You could do forces, but I think energy is just easier. Energy is the more dominant theme. So it starts out with mgh. We know we're going to lose the work done by friction, and so that's mu m1g cosine theta. Remember, this is the normal force of a box on a ramp. Mu times the normal force. That piece is the force of friction. And now we need the distance on the ramp. The distance on the ramp is going to be h divided by sine theta. Again, you're not given the distance, you're given the height. So you have to find the distance. In that case, we know that d equals, h divided by sine theta is the distance. And we know that energy converts then to kinetic. So we can find the velocity of the box right as it hits the bottom of the ramp. Now we get into projectile motion, okay? So this is our classic projectile motion equation, right? And the key piece here is we know the height is capital H, and this has to be negative. Again, this thing is going to be launched down on the ramp, and then we know that gravity just is a 1/2 gt squared. Go ahead and just use your calculator, right? This is just plugging, it's just a quadratic. You could use the quadratic formula if you wanted, or you can just graph it and just figure out the time it takes for it to reach a height of 0. The horizontal position, we know now, if we know that the ball is in the air this long, and we know how fast it was moving, well, we know how fast horizontally it was moving. Remember, V naught cosine theta is how fast it's moving horizontally, and that's how fast it would move the whole time in the air, times the time would then give you the horizontal distance. Okay, when M2 is just chilling there, hooked to this rope, so it's hooked to, it's being held by these two things before T1 kind of gets sliced. If we wanted to find these, all we have to do is vectors. We know that all the forces have to cancel. And so in the x direction, T2 cosine theta is pulling it to the right, T1 is pulling it to the left, and since it's not accelerating, those forces have to cancel. Vertically, T2 sine theta is pulling it up, and M2g is pulling it down, and those have to cancel. This is just a system of equations with two variables and two unknowns, so I just say solve with algebra. So we can figure out T1 and T2. Okay, then we know the rope gets sliced, and so we're going to release this thing, and we want to figure out how fast it's moving before it ends up colliding, and so we want to do energy. This normally is L minus L cosine theta, but you got to be careful because they didn't give you the vertical angle, they gave you the horizontal angle, so the sine theta is actually going to be L sine theta here is going to be that difference. So be really careful of what angle is given. Generally on the pendulum, guys, we use the vertical angle, and then we can do L minus L cosine theta. But in this case, that's not what they gave us, so we have to adapt. So this is the velocity of it before the collision. If we want to find the tension right before the collision, we know that it's vertical, and we know that its tension's up, M2G is down, and T minus mg equals ma, where a is v squared over r. So we can find the tension at that moment. Now there's a collision. Okay, now this collision is going to cause a rotation. So this one is all about angular momentum. And so the angular momentum at the beginning, we treat it as a point particle. And so when M2 is flying in, we want to think of it as R cross MV. Don't worry about the cross product because the velocity and the lever arm are perpendicular. And so we just get M2 times how fast it's moving, and we're told that it hits the board at 2/3 of L. So the 2/3 of L is then the lever arm, and then it's going to hit and stick. So then the moment of inertia of this system is the sum of the two pieces. So it's the ball, which is this mr squared term, and the 1/3 ml squared for a board pivoted at the bottom. Okay, so then we do conservation of angular momentum to figure out how fast this thing is rotating just after the collision. Okay, so that'd be that value. That's how fast this thing is rotating. All right, let's go back. So we have M2, we hit this thing, about right there, and it's got angular momentum that's going to cause this thing to rotate. Well, now we want to know how fast it's going to be moving at the bottom, because the board's going to rotate down, and now it's all about the swing. Now it's about energy. The energy at the very beginning. Okay, so we know how fast it's rotating. So after the collision, that's how much energy we have in rotational energy. Plus, the board and the ball are both going to lose gravitational potential. Okay, how much does the board lose? Well, how much does the center of mass of the board change? It changes by L over 2. How much does the ball lose? Well, it loses it all. The ball is at a height of 2/3 of L, and it's going to go down to the ground. So it's the rotational energy that the system possesses after the collision, plus the board's loss of potential, plus the mass, the potential energy of the ball. That will lead to the final rotational energy that the system has right before it hits the ground. And that's this omega 4, this 3.35 radians per second. Okay. All right. That hits, the scissor cuts the string. And now we're looking at a system of equations. Again, this is the annoying part. So if you look at the left side, T4 is going to be bigger than M4G and cause M4 to accelerate up. On the right side, M5G minus T5 equals M5A. So the weight of M5 is going to be bigger than the tension. And then if we look at the torque on the pulley, this bottom thing right here, this is torque equals I alpha. The torque is the difference between T5R and T4R, right? The right side of the rope is, both lever arms are R, but the right side is going to be a bigger torque, causing this thing to rotate clockwise. And then it equals I alpha. We know alpha can be A over R, and I for a pulley. Pulleys are considered to be discs unless otherwise stated, and so then it's a 1/2 mr squared. We do some algebra to solve for all that stuff. We find the tension. Well, actually, we probably find A first. But with A, we can find alpha and tension. And then if we want to know how the time it takes, well, we can just do D equals 1/2 AT squared. Remember, don't put a G here. It's not in free fall. We know this thing isn't falling as fast as it would be in free fall. It's going to rotate down a little slower, so we can use this to find the time. And if you want to know the velocity, you could use energy, you could use the v squared equation, or you could just use this, knowing the initial velocity is 0. And once you know the acceleration rate and you know the time, you can just figure out how fast it must be moving at the bottom. Okay, so a lot of things going on there. Try to write it so it was obviously complicated on purpose to make you really think about all the old school mechanics things. But there's energy, there's forces, there's circular motion, there's torques, there's angular momentum with a collision. So a lot of good stuff. Make sure you can handle this question.